Good afternoon, class. Today we will begin Chapter 9, looking at Section 9.1, comparing two population means. Let's first recap. A confidence interval is just an interval estimate with a confidence level for a population parameter. When creating a confidence interval for the population mean mu, we calculate x bar minus e, x bar plus e. So this is our left endpoint of our interval, and this is our right endpoint of our interval. The margin of error e depends on whether the population standard deviation sigma is known or unknown. Since this will change our formula, one uses the z distribution, table B, and one uses the t distribution, table C. If sigma is known, we are able to use our critical z value, right? This is our table B. If unknown, we use our critical t value. This is our table C. Now, it is often desirable to compare two population parameters in order to identify if they are significantly different. To do so, we will look at their difference. Suppose you thought that there was no difference between two population parameters. That is, they were the same. If this was the case, then subtracting the two values should give you the number 0. However, if you thought one was larger than the other, when you subtract the smaller from the larger, you would expect to get a positive number. Our technique for this section, construct a confidence interval for the difference between two population means. We will denote the two means by mu1 and mu2. These will represent the population means for the first population, 1, and the second population, 2. So we may write the difference as mu1 minus mu2. When we are dealing with two populations, we need to consider how data from the two populations are connected, if at all. Two samples are said to be independent if the data from the first are not connected to the data from the second sample. Two samples are dependent if the data from both samples are systematically connected or paired. A quick example. If we compare the mean ACT score of high school seniors entering college to the mean ACT score of adults returning to college, then the data sets would be independent. This is because each student has their own score. However, if we look at sets of grades on a pre-test and post-test administered to the same group of students, then the data sets would be dependent. This is because each student has an associated pre-test score and post-test score. So we can think of this kind of as paired data. Each individual in the sample has two data values associated to them. For our class, we will only consider independent samples. In this case, our confidence interval for the difference between two population means is given by our point estimate. Remember that we're creating a confidence interval for mu1 minus mu2. And we already know that the sample mean is a good point estimate for the population mean. So if we have two population means, we can create two sample means. And if we're looking at the difference, we might as well look at the difference in the sample. So here is our point estimate, x bar 1 minus x bar 2. And to create our interval, we're going to subtract our error and we're going to add our error. So nothing has changed here except for the fact that we're estimating something new, so our point estimate changes. Now, of course, since we're doing something new, our error is also going to change as well. And the right-hand side of our exam formula sheet is going to consist of our Chapter 9 error formulas. Okay? So this tells us that the best point estimate for the difference between population means, mu1 minus mu2, is the difference between sample means, x bar 1 minus x bar 2. And that should make sense. The only new formula is our margin of error, E. Just as we saw with a single population mean, the formula depends on whether sigma is known or unknown in both populations. We will denote these by sigma 1 and sigma 2. So a fact, when both population standard deviations are known, the samples taken are independent, simple random samples, and either both sample sizes are at least 30 or both population distributions are approximately normal, the margin of error of a confidence interval for the difference between two population means is given by this nasty formula. So when sigma in both populations are known, we're going to use a z-value. And we're going to incorporate our sigmas in the formula, just as we saw in section 8.1. Recall that our critical z-value can be found at the bottom of table B. We will use the three-step process. So step 1, find the point estimate. In this case, it's x bar 1 minus x bar 2. Step 2, calculate our margin of error E using the previous formula. And then step 3, put it all together and find the lower endpoint and upper endpoint by subtracting and adding our error to and from the point estimate. Let's look at an example. A researcher is looking at the study habits of college students. A random sample of 42 freshmen reported a mean study time of 15.0 hours per week. A random sample of 39 seniors reported a mean study time of 23.0 hours per week. Construct a 95% confidence interval to estimate the true difference between the amounts of time per week that freshmen and seniors spend studying. Assume that study times for freshmen have a population standard deviation of 4.7 hours per week, while the study times for seniors have a population standard deviation of 5.2 hours per week. Now, we first notice that we have two groups given in this problem, right? We have the freshmen and we have the seniors. Since freshmen are mentioned first in the problem, we will let population 1 be freshmen and population 2 be seniors. This will help us with our notation. So x bar 1 is going to be the sample mean for freshmen, mu1 is the population mean for freshmen, and sigma 1 is the population standard deviation for freshmen. Similarly, x bar 2 will be the sample mean for seniors, mu2 the population mean for seniors, and sigma 2 the population standard deviation for seniors. Find the point estimate x bar 1 minus x bar 2. This is our first step. So in the problem, if we go back, a random sample reported a mean study time of 15 hours for freshmen. So this is our x bar 1. And then here we reported a mean study time of 23 hours, and this was coming from our sampling of seniors. So x bar 1 minus x bar 2 gives us negative 8.0. Our second step, we want to find the margin of error using the formula. In the problem, we are asked for a 95% confidence interval. If we look at our table B, 95% represents a z-value of 1.96. So that's where this value is coming from. Now also in the problem, we're saying assume for freshmen, the population standard deviation, this is our sigma 1, is 4.7. And furthermore, for seniors, our population standard deviation, this is our sigma 2, is 5.2. So Sigma 1 is 4.7, sigma 2 is 5.2. Finally, our N1 is the sample size of our freshmen, and we saw that we sampled 42 freshmen. N2 was our sample size of seniors, and we saw that in the problem we sampled 39 seniors. Using our calculator, we get 2.164257. Putting this together, our lower endpoint is our step 1 value minus our error, which is step 2, and we get approximately negative 10.2. Our upper endpoint of our interval is our point estimate from step 1 plus our error from step 2, and we get approximately negative 5.8. This gives us the interval negative 10.2 to negative 5.8, meaning we are 95% confident that freshmen study between 5.8 and 10.2 hours per week less than seniors. Okay, let's think about why we interpreted it that way. What were we estimating? We were estimating the difference, subtracting. Notice that when we subtracted, we got an interval range of negative values. When we get negative values subtracting, that tells us that this number has to be bigger than this number. If this number is bigger than this number, that means that seniors study more than freshmen. Or another way to put it, how I phrased it here, is that freshmen study less than seniors. How much less? On average, this much less. Right? So the negative kind of represents a less than result. Okay? If you have any questions on this, you can post in our discussion board or again, email me. I've only done one example in these sets of slides because, again, confidence intervals, it's the same process. The hardest part of these problems is reading the problem. Now, since there's 2 populations and 2 samples happening, the problems are going to be longer. But the most difficult part of these problems is not only finding the numeric values and pulling those numeric values out, but finding the numeric values and correctly labeling those numeric values. Once you label the numeric values, plugging them into the formula becomes very, very easy. Okay? So it's the same process as we saw in chapter 8. It's just a different formula. So if you have any questions, if you're struggling, if you would like to see a couple more examples, there's some posted in our section 9, in our chapter 9 breakdown, our section 9.1. There's more written problems that you can read and follow along with. Or of course you can email me and we can schedule a meeting and go over problems from your homework, or I can send you solutions to arbitrary problems from the book if you just want to see more.